Every time you type a website name into your browser, an invisible system springs into action to translate that name into an address a computer can actually reach. And today, we're pulling back the curtain on how it works. Welcome to Lesson 34 of our IT Networking Mastery curriculum, a deep dive into DNS, the domain name system. Over the next few slides, we'll trace the journey from a human-readable name like example.com all the way down to the IP address your device connects to. And along the way, you'll see why this seemingly simple lookup is actually one of the most fascinating pieces of internet infrastructure. Before we dive in, here's the roadmap for our journey. We'll start at the top with the DNS hierarchy, the root servers, the top-level domains, and the authoritative name servers that actually hold the answers. From there, we'll unpack the record types you'll encounter daily, like AAAA, CONAME, and MX. Then we'll walk through the resolution flow itself, comparing recursive and iterative queries before finishing with the practical glue that makes DNS fast and trustworthy, caching, TTLs, and DNSSEC. So let's start at the top of that hierarchy. DNS is structured as an inverted tree, and right at the peak sits the root, represented by a single dot and served by just 13 logical root server clusters worldwide. The root doesn't know where google.com lives, but it knows who runs .com, and it points you to the top-level domain servers for .com, .org, .chu, .io, and so on. Those TLD servers, in turn, delegate to the authoritative name servers for each registered domain, which finally hold the actual records for hosts and subdomains like www.google.com or shop, Dargslan, Chu. Each level only knows the next, and that's exactly what makes DNS scale. Now, once those authoritative name servers are reached, what do they actually hand back? Records, and each record type answers a different question. An A record maps a name to an IPv4 address, while DE does the same for IPv6. CNAME creates an alias from one name to another. MX points mail to the right server, and TXT carries arbitrary text used for things like SPF and DKIM email authentication. NS declares which name servers are responsible for a zone, SOA holds the zone's metadata, and PTR does the reverse lookup, turning an IP back into a name. And notice that TTL column on the right. It tells resolvers how long they're allowed to cache each answer, which becomes important in just a couple of slides. So let's trace a real lookup end to end. Your browser asks its local resolver, maybe your ISP's, or 1.1.1.1, or 8.8.8.8. Where is google.com? That resolver then walks the hierarchy we built earlier. It asks a root server who handles .com. The root points it to the .com TLD servers, and the TLD points it to Google's authoritative name server, NS1, google.com. Only that authoritative server actually knows the answer, and it returns the A record, 142.251.18746. The resolver caches it, respecting the TTL we just talked about, and hands the IP back to your browser. Now, that whole journey actually uses two different query styles, and it's worth pulling them apart. When your laptop talks to its resolver, it's making a recursive query. Basically, just hand me the answer, I don't care how you get it. The resolver does all the legwork, but when that resolver turns around and starts climbing the hierarchy, it switches modes. It asks iteratively. Each server it contacts, root, then TLD, then authoritative, doesn't solve the problem. It just gives a referral saying, I don't know, but try them. The resolver chases that chain itself, hop by hop, until somebody finally returns a real answer instead of another pointer. Now, if every lookup actually walked that full chain, the root servers would melt within seconds, which is why caching is woven into every layer. Your browser holds answers for a few seconds or minutes, your operating system's resolver keeps its own store, and the big public resolvers like 8.8.8.8 or 1.1.1.1 cache aggressively too. What governs how long each copy lives is the TTL, set by the authoritative server itself. A typical web record sits around 5 minutes to an hour, short enough to stay fresh, long enough to spare the resolvers. And here's the catch. There's no real cache invalidation in DNS. Before a migration, you lower your TTL to 60 seconds a day ahead, let the world's caches drain, then raise it back afterward. With that mental model in place, let's get our hands dirty. The tool you'll reach for again and again is Dig. A plain query to google.com returns an answer section showing the A record, its TTL of 300 seconds, and the IP. Add a record type like MX, NS, or TXT to ask for mail servers, authoritative name servers, or things like SPF entries. The plus trace flag walks the full chain from root to TLD to authoritative, letting you watch the journey we just described. And by prefixing an abwurm with a resolver address, you bypass your local cache to query Cloudflare or Google directly, invaluable when you suspect stale data. Now, Dig is great for inspecting answers, but how do you know those answers are actually genuine? Plain DNS travels unencrypted over UDP port 53 with no integrity check, which is exactly how cache poisoning attacks like the famous Kaminsky exploit in 2008 worked. DNSSEC fixes the trust problem by having each record cryptographically signed, with those signatures carried in RSIG records and a chain of trust running from the root down through the TLD to the domain. One important nuance: DNSSEC proves authenticity. It doesn't encrypt. That's a separate job handled by DNS over HTTPS or DNS over TLS. So let's talk about that privacy side. DNS over TLS, or DOT, wraps your queries in a TLS tunnel on TCP port 853, encrypted but still easy to spot on the network. DNS over HTTPS, or DOH, goes a step further by writing on port 443, blending right in with normal web traffic so a network operator can't easily tell DNS from any other HTTPS connection. Keep the critical distinction in mind. DNSSEC proves the answer is real. DOH and DOT keep the question private. For real security, you want both. Now, even with all that theory in place, DNS in the real world has a handful of traps that bite engineers again and again. A high TTL during a migration means caches cling to the old IP for hours. Drop it to 60 seconds the day before, then raise it back. Names at the apex are forbidden by the RFC, so reach for an alias or enemy record instead. Trailing dots matter in zone files. MX records must point at a real A or AA host name, never a CNAME. And remember, even does not exist, answers get cached, so a fresh domain can take time to surface. So let's pull the whole picture together. DNS is a distributed hierarchical database. Root, TLD, authoritative, host, and it speaks through a small vocabulary of records. A and AA for addresses, CNAME for aliases, MX for mail, TXT for policy, NS for delegation. Resolution happens recursively from the client side and iteratively behind the scenes, with TTL deciding how long answers linger in cache. And to keep it trustworthy, layer DNSSEC for authenticity with DOH or DOT for privacy. Together, not instead of each other. And here's your quick reference to keep nearby. Notice the shape of it. Hierarchy at the top, then root servers and transport, then the record types you'll actually type into a zone file. A and I for addresses, CNAME for aliases, MX for mail, TXT for policy, NS for delegation, and PTR for the reverse lookup that turns an IP back into a name. Screenshot this one. It's the lesson in a single glance. And that wraps up our journey through DNS, from the root all the way down to securing the answers with DNSSEC. Next up in Lesson 35, we shift gears from names to numbers, DHCP at an advanced level, paired with IPAM, the discipline of managing IP address space at real-world scale. If this lesson helped things click, head over to dargslan.com or the YouTube channel, and I'll see you in the next one.